Welcome back. In the last video, we saw how logics comprise a semantics, a syntax, and a deductive system. And in this video, we're going to be looking at the semantics of logics. And in particular, we're going to be looking at the relationship between the semantics and the real world, and how the semantics models the real world. In the next video, we'll take a look at the syntax and look in more detail at how the syntax and semantics relate to one another. There is a bit of a circular dependency between the syntax and the semantics, and so we'll look at this link in the next video, but we will start to see some of the syntax creeping in this time. So to start off with, I thought it would be useful to look at some intuitive examples from real life, things we're familiar with, rather than diving straight into the logic. And the first example of modelling I'd like to show is one with which we're all very familiar, the idea that we can estimate the time it will take a car travelling at a speed u, going a distance s, to travel that distance. And we can do this using the equation time equals the distance over the speed. We're familiar with this from real life. Perhaps you use SatNav or Google Maps to work out how long it's going to take to complete a journey. But the interesting thing about this example is not what it does show, but rather what it doesn't say about the real world. So for example, we're not taking into account any acceleration or deceleration of the car. We're not thinking about what happens when the hill is bumpy. The road is bumpy. We're not thinking about traffic jams or stops for petrol or brakes on your journey. We're modelling the real world in a simplistic manner. And all of those things will affect the speed of the car, but if we've got a good idea of the average speed, then we can get a relatively good idea of the time it will take us. An example perhaps more familiar to computer scientists is the idea of modelling programming languages. So here we see two statements from some made-up dummy programming language, a while statement and the result of assigning an expression 2 plus 5 to the variable x. Now one way we could model what this programming language does, what the effect of each of these statements is to think about the effect they have on the processor, or specifically the values in the registers in a processor and the values in RAM, in main memory. Or we could say, well, actually, a processor is generally 32, perhaps 64 bits wide, and this data width causes us some confusion sometimes. Integers may wrap round, they may overflow, they may do things that we don't really want the complexity of reasoning about. So maybe instead of modelling the effect of these statements on the processor, we could abstract a bit. And we could say, well, let's actually talk about mathematical integers, which don't have the problem of being constrained by fixed bit widths, and we'll let the compiler deal with all that complexity. The point of showing you both of these examples is to illustrate that when we model the real world, we're actually leaving out a fair bit, but it's the idea of creating a useful model with which we can reason about the real world, which I want to illustrate here. So let's go on to our long-running example, which we'll see in the next few videos, of propositional logic and what the semantics of propositional logic are. And logics overall, ultimately, are concerned with reasoning about truth. We want to know whether certain sentences are true or false. So here's some examples. The sentence, "It is raining." It's a natural language sentence, and it could be either true or it could be false, depending on when you look out of your window. We're not reasoning about time here. We're not saying it is raining now, but it might not be in the future. It's simply an assertion which may be true or false. Other logics, such as temporal or modal logics, do deal with time or progression of time in a certain way. Propositional logic doesn't do that. And again, this is an example of something which propositional logic makes a decision about, how to reason about the real world. Here's another example. 2 is bigger than 5. Now, under pretty much any reasonable understanding of what this sentence means in natural language, this sentence is probably going to map to false. We don't just have to apply this to natural language sentences, we can apply it to, for example, circuitry. So we're asking the question, is this wire at 5 volts above ground? There are some things we don't model. So, for example, we don't model a third unknown value along with true and false. In this final example here, perhaps one of these wires has been cut. It's left floating. It's not tied to either 5 volts, positive, or ground. Propositional logic doesn't model this. Other logics do. 3-valued logic, for instance, is sometimes a useful logic to reason about digital circuits. And in a similar vein, we don't think about probability. We don't have an infinite number of values between true and false. All this, perhaps, in another logic is something we might want to think about. So going on to some specifics of propositional semantics. We don't want to actually concern ourselves with the complexities of the natural language we see in these sentences or the specific domain of electronics we see in this example. We want to abstract from them slightly. And so what we do is say, well, instead of thinking about specific instances of sentences, specific instances of things we want to model, we'll abstract away from that and simply represent things with A and B. We'll see more of this in the next video, but for the minute think of A and B like the sentences we've just been looking at, to which we can assign truthood values. And if you're a computer scientist or a mathematician perhaps, you can probably see what's coming next. We're going to assign each value of true and false to A and B. We're going to represent them with 0 and 1, and we find there are 4 possible combinations. And what we're going to do now is say, well, simply having these sentences on their own is slightly useless. We want to be able to combine them in some way, using natural language connectives such as AND or OR. And again, if you're a computer scientist, you can probably second guess what's coming. We're going to define some truth tables. And I won't go into too much detail on the actual truth tables, because you may well be already familiar with them, and if you're not, there are tons of resources out there which deal with them anyway. What I'm going to do is look at some specific instances of values in these truth tables which are interesting to us. So to very briefly start off, we're going to define AND, the connective AND. So for example, if A is the sentence, or A represents the sentence, the sky is blue, B represent the sentence, the grass is green. So the compound sentence, the sky is blue and the grass is green, is true. 1. Note this little hat symbol here is a shorthand for AND. And we're going to define that more rigorously in the next video. This is actually part of the syntax of propositional logic. For the minute though, just think of these columns as representing natural language sentences. The other 3 values in our AND truth table are 0. Because in each of these cases, at least one, of A and B is false. So for instance, this second line, A might represent the sentence, the sky is blue, but B might represent the sentence, the grass is red. So the sentence, the sky is blue and the grass is red, is clearly false. Next, we're going to take a look at a second connective or. And this one is slightly more interesting because it starts to show us how propositional semantics models the real world and makes some design choices whilst doing so. So these are the truth table values for or. If at least one of A and B is true, then A or B is true. But if neither are true, if both are false, then A or B is also false. And the interesting value in this truth table is the top one. We could quite reasonably have said, well, we want this value to be 0, because that links in more naturally with our natural language intuition of the word or, which quite often means either something or the other, but not both. This is actually the difference between the propositional connectives or XOR, exclusive OR. Next, we're going to take a look at not. And this is a fairly intuitive one. If A is true, then not A is false, and vice versa. If A is false, not A is true. We're going to skim past this one and go on to our final connective, which is the idea of conditional. So if then. So for example, if it is raining, then the pavements are wet, where it is raining is A and the pavements are wet is B. And we call this implication, so we denote this by saying A implies B. And the first value in this table is relatively intuitive. It's the example we've just seen. If it is raining, then the pavements are wet is true. On the other hand, if I look out of my window and I see, yes, it is raining, A is true, but B, the pavements are wet, is false. If the pavements are actually dry, then we don't have this conditional. This conditional turns out to be false. And so we represent that with 0, with falsehood in our semantics. The two interesting cases are these last two, where A itself is 0. So in the sentence, if it is raining, then the pavements are wet, A is false, I look out on my window and it's not actually raining, then this sentence doesn't make any claim about the status of the pavement. There's no else clause in here like you might expect in a programming language. So this begs the question, well, what should we assign for these last two values? And as you can see here, we assign truthhood. We assign the value 1. And this begs the next obvious question, why? Why have we assigned true and not false to these two values? It seems relatively arbitrary. And I won't go into too much detail on why here. This notion is known as vacuous truth, if you'd like to go and look it up. But the two key points to take away are, firstly, that assigning 1 to these values is useful when we come to look at our syntax and particularly our deductive system. In other words, assigning 1 to these values is useful for reasoning about the real world. It's used particularly in mathematical proof, specifically proof by induction a lot of the time. It's also a reasonable model of the real world. And these two things combined mean that assigning 1 to these values is a sensible choice. A similar notion, again looking at modelling the real world, is the idea of causality. Our values in our truth table here don't have any notion that A must it be in some way related to B. So for example, the sentence, if the sky is blue, then the grass is green, it is true under our semantics. It's this first entry here. But there's no obvious causal relation between the sky being blue and the grass being green. So the point of showing you all this was to show you that there are design choices to be made when we're modelling the real world. and these design choices should be both useful for us to reason about, but also be a useful model of the real world. And many logics use propositional logic, these kind of truth tables, for a base and build off them and add more and more complexity to them to reason about more and more complex things in real life. So in this video, we've taken a look at the semantics of propositional logic and looked at semantics in logics in general. And then in the next video, we're going to be taking a look at the syntax of propositional logics and logics in general and relating them to the semantics.